Hey there, let's begin our 8th recitation. Well, it looks like we'll need some whiteboard space first. I'm sure that the graduate student or students who did this will certainly not be needing it. So I'm going to do them the favor of erasing it without asking first. 9.1.3. We're given a set as the set of these four numbers, 1, 2, 3, 4. And we're given a relationship, 2, 2, 2, 3, 2, 4, 3, 2, 3, 3, and 3, 4. And it wants us to tell whether this relation on the set is reflexive, symmetric, antisymmetric, and or transitive. So first, it's important to recognize the many different ways we can see a relationship depicted. We can depict a relationship on a set like this, very simply, just the numbers. We can depict it a little more visually as well. We can depict a relationship with a matrix. So because we have four numbers in our set, we would have four columns and four rows and four columns. For any pair that exists in a relationship, we would have a 1 at that intersection in our matrix. So we have 2, 2, therefore going down 2 and across 2, we have a 1. This relationship at this position, 2, 2, exists. We have 2, 3, so down 2 across 3. 3, 2, that's down 3 across 2. 2, 4, 3, 3, and 3, 4. If a relationship does not exist, it's not depicted in our relationship up here, this is shown by a 0 in our matrix. So then we can also depict our matrix, our relationship, with a digraph. So because there are four numbers, we have four nodes, we'll number them. We have 2, 2, meaning that node 2 points to itself. We have 2, 3, so 2 points to 3. 2, 4, so therefore 2 points to 4. 3, 2, so 3 points back at 2. 3, 3, and 3, 4. So 1 is still depicted in our digraph, even though it does not have a relationship with the other nodes. Similarly, 1 has a node and column, even though they're all zeros in our matrix. So if this relationship is reflexive, then these are also reflexive. If it is symmetric, then these are also symmetric. And there are different ways of eyeballing the matrix or looking at the digraph to determine whether it's reflexive, symmetric, antisymmetric, and or transitive, but for the sake of the first few of these problems, we're only going to be looking at these numbered sets with pairs. And by looking at these, determining whether this relationship is any one of these properties. Just to keep it simple, we're not going to really look at these quite yet. Okay, is it reflexive? Well, it's reflexive if for any variable a comma a, where a exists in our set, so let's say our set is just S, a comma a exists in our relationship. And that's really just a fancy way of saying that for any number up here, you have to have it reflect back on itself. We have 2 reflecting back on 2, we have 3 reflecting back on 3, but we don't have 1 reflecting back on 1, and we don't have 4 reflecting back on 4. So because 1, 1 is not in the relationship, it is not reflexive. Is it symmetric? It's symmetric if for any variable a comma b that exists in our relationship, the opposing reverse pair also exists. So then b comma a must exist for it to be symmetric. Does this condition satisfy this relationship? Or does this relationship satisfy this condition? No, because we have 2, 3, and we have 3, 2, that's symmetric. So it's symmetric in one case. However, 2, 4 does not have a 4, 2 to complement it. So it's not symmetric. We have 2 comma 4 in our relationship, but we don't have 4 comma 2 in our relationship. So it fails being symmetric in one case, so the entire relationship is not symmetric. Is it antisymmetric? It's antisymmetric if for A comma B, which exists in our relationship, the opposing pair, B comma A, must not exist in our relationship. It has a hint of antisymmetry. For example, we have 2 comma 4 and we don't have 4 comma 2, but because we have at least one reflexive pair, we have 2 comma 3 and 3 comma 2, we have a case of symmetry. So it's not antisymmetric in all cases and therefore not antisymmetric. So we have 2 comma 3 in our relationship, but we also have 3 comma 2 in our relationship, therefore not antisymmetric. Is it transitive? So this is a little more confusing. Basically the rule here is if A comma B is in our relationship and B comma C is in our relationship, then A comma C must also exist in our relationship. So this is kind of easy to eyeball. We have 2 comma 2 and we have 2 comma 3, for example. We need to look at all of the pairs whose right side, whose right value matches another pair's left value. So this pair has a 2 on the right. This pair has a 2 on the left. So because the right here matches the left, that means that this pair's left must exist in a pair with this pair's right. So basically, 2 comma 3 must be a pair somewhere in our relationship. This pair's left must point to this pair's right. And of course, that's satisfied by this relationship. So that's okay, that's transitive. We have 2 comma 2 and 2 comma 4, so therefore 2 comma 4 must exist, and it does. We have we have 3 comma 3 and we have 3 comma 4, therefore 3 comma 4 should also exist, and that's satisfied by this one here. So I believe it is transitive in all cases. So therefore, we would say yes, it is transitive. So it's worth mentioning that antisymmetry has kind of a reflexive property attached to it. So what I mean by that is that the definition of antisymmetry is that if A and B are in a relationship and B comma A is in a relationship, then A is equal to B. That is to say, the only time a symmetric pairing is allowed in an antisymmetric, and then for the antisymmetric property to still hold true, is when A and B match. It can only allow symmetry when both of the values are equal to one another. So basically, antisymmetry has an added kind of reflexive property attached to it. Okay. So even if you see something like 1 comma 1, it could still be antisymmetric. You have to really check the ones where the 2 values of the pair are not equal. All right. So is this set reflexive? Looks reflexive to me. 1 comma 1, 2 comma 2, 3 comma 3, 4 comma 4. Is it symmetric? Well, it is symmetric. 1 comma 2, 2 comma 1. And that's the only pair we have to check. Is it antisymmetric? No, because we have a case of symmetry. So for the same reason why it is symmetric, it is not antisymmetric. Is it transitive? Right, well, we don't have that many values to check, but for any case where the right-hand side of a pair matches the left-hand side of another pair, clearly transitivity holds. So for example, we have 1 comma 2. We have 2 comma 2 as well. So therefore, 1 comma 2 should exist in our relationship, and it already does. So we can see that in all cases it's transitive, therefore the relationship is transitive. How about this one, 2 comma 4 and 4 comma 2? Is it reflexive? No, because we'll give an example. 3 comma 3 is not in the relationship. Is it symmetric? Yes. It only has one possible pairing to check whether it's symmetric or not. 2 comma 4 and 4 comma 2 does exist. So yes, it is symmetric. For that same reason, it's not antisymmetric. It is not transitive, right? So we have 2 comma 4 and 4 comma 2. That means that 2 comma 2 should exist as a pairing. It does not. Furthermore, we have 4 comma 2 and 2 comma 4. That also means that 4 comma 4 should exist as a pairing. So by counterexample, it's not transitive, right? Is it reflexive? No. Does not have 1 comma 1, for example. Is it symmetric? Also no. We have 1 comma 2, but we don't see a 2 comma 1. Is it antisymmetric? Because we don't have a single case of symmetry. We have 3 comma 4, but we don't have a 4 comma 3. We have a 2 comma 3, but we don't have a 3 comma 2. We have a 1 comma 2, but we don't have a 2 comma 1. So in all cases, it's not symmetric. So the entire relationship is not, or it is antisymmetric. Is it transitive? It is not transitive. We have a 1 comma 2 and a 2 comma 3 in our relationship, so we should have a 1 comma 3, but we don't. So therefore, not transitive. Okay, part E, reflexive. Well, clearly, 1 comma 1, all the way through 4 comma 4, so it is reflexive. Is it symmetric? Yes. We don't really have any pairs where they differ, so there's nothing to check against, if that makes any sense. It is symmetric. We only have to check for symmetry when there is at least one pair where the two sides don't match. So if there was like a 2 comma 1 in there, then we'd be looking for a 1 comma 2. But because there's nothing to check at all, it's kind of like an if statement. If there's a pairing, then the reverse pairing should exist. But the initial pairing doesn't exist at all. So the if statement is always true. So that's why it is symmetric. It's also antisymmetric for the same reason. There's no there's no pairings to reverse to check whether it's antisymmetric or not. So the if statement always passes. So it is antisymmetric. Transitive for the same reason. There is no two pairings where the left-hand side matches the right-hand side. So you can't combine them into some transitive if statement. So because there's nothing to check at all, we would say yes, it is also transitive. Finally, part F. Is it reflexive? It is not reflexive because we don't have, for example, 2 comma 2. Is it symmetric? Right, it is not symmetric because we have 1 comma 4, but we don't have 4 comma 1, so it fails symmetry in one case. It's not symmetric. Is it antisymmetric? Well, it's also not antisymmetric because it has 1 comma 3 and 3 comma 4, so it fails to be antisymmetric in one case. There's a hint of symmetry in there. So no, it is not antisymmetric. Finally, it is also not transitive. We have 1 comma 3, we have 3 comma 1, both in our relationship. Therefore, 1 comma 1 should also exist in our relationship, but we've already shown, or we already see, it does not. So no, it is not transitive either. Okay, so let's do this next one. We have this statement, this English statement, with people replaced with variables, and we want to determine whether it's any of the following properties. So it's a lot easier than it sounds. Is it reflexive? Well, remember it's reflexive if A comma A exists in our relationship. So just ask yourself, does the following statement make any sense? A is taller than A. Does that make any sense to say? Well, no, because A can't be taller than him or herself. So no, it is not reflexive. Is it symmetric? If A is taller than B, does it also make sense to say that B is taller than A? No. If A is taller than B, then there's no way for B to be taller than A. Right back at him, so is it anti-symmetric? Yes, for the same reasoning that it's not symmetric, it is anti-symmetric. If A is taller than B, then there's no way that B is taller than A. Is it transitive? Okay, so yes, it would be. So let's imagine that we have some third party named C. A and B exist in our relationship, meaning that A is taller than B. B and C also exist in our relationship, that is to say that B is taller than C. Does it also make sense to say that A is taller than C? These two in a relationship would imply that A and C is also in our relationship. And that does make sense to say. It does make sense to say that A is taller than C. Okay, so part B. A and B were born on the same day. Does it make sense to replace B with A for the reflexive property? Does it make sense to say A and A were born on the same day? Right, it would still hold true, so I would say that makes sense. It is reflexive. If A was born on the same day as A, then there's no contradiction there. Is it symmetric? Can we also say, assuming this is true, B and A were born on the same day to switch the two variables? Absolutely. It is symmetric. For the same reason it's symmetric, it is not anti-symmetric. Is it transitive? Yes, so we can again replace it. We can say that A and B are in a relationship. B and C are in a relationship. Therefore, A and C must also be in a relationship. Simply put, A, B, and C can all be born on the same day. So therefore, it is transitive. Okay, next. A has the same first name as B. Is it reflexive? Does it make sense to say that A has the same first name as A? Right, it still holds true. I have the same first name as myself. So yes, it is reflexive. If A is the same first name as B, then does B have the same first name as A? Yes, so it is symmetric. Is it anti-symmetric? Right, no, because we could have two different people who both have the same first name. So it's not anti-symmetric. Okay, is it transitive? If A has the same first name as B, and B has the same first name as C, then do A and C have the same first name? And yes, right. A, B, and C can all have the same first name. So it is transitive. So for this one, we'll go through it quickly. A and B have a common grandparent. Yes, it can be reflexive. Yes, it is symmetric. For the same reason it's symmetric, it's not anti-symmetric. Is it transitive? Well, let's think of it this way. If A and B have a common grandparent, and B and some other guy named C also have a common grandparent, then do A and C have a common grandparent? No, right? Because A and B could have one common grandparent. B and C could have a different common grandparent. That doesn't necessarily mean that A and C have that same common grandparent. So, for that reason, this is not necessarily in the relationship. I mean, it might be sometimes. Maybe A and B have the same grandparent as B and C, in which case it would be transitive. But that doesn't mean it's transitive in all cases. So no. Okay, so now we want to determine whether certain functions or equations are any of the following properties. And it's easier than you think. Let's do the first one together. We're going to be doing them all together, but you know what I mean. We have x plus y equal to 0. Is it reflexive? That is to say, does x plus x always equal 0? Well, obviously not, right? If x is 1, for example, then is 2 equal to 0? No. And our counter example then would be to say that 1 comma 1 does not exist in our relationship. Is it symmetric? That is to say that if x plus y is 0, then is y plus x equal to 0? All we're doing is replacing the x and the y with each other. And the answer is yes, right? It is symmetric because addition is commutative. You can flip the two numbers and it's still the same thing. Okay, is it anti-symmetric? Well, we're going to see no, it is not. For example, we can set x equal to 2 and y equal to negative 2. Now let's plug those in and see. Well, 2 plus negative 2 is equal to 0. But then also, negative 2 plus positive 2 is also equal to 0. This above equation is the original, x plus y equals 0. This bottom one is y plus x is equal to 0. So we have symmetry here. Therefore, it is not anti-symmetric. Is it transitive? Is it transitive? Well, we can show it's actually not transitive. So let's give a counterexample. We have the relationship 2 comma negative 2 in our relationship. 2 plus negative 2 is 0. We have the relationship 2 comma, or negative 2 comma 2, which is also in our relationship. But we don't have the relationship 2 comma 2. This is not in our relationship. 2 plus 2 is not 0, it's 4. So no, it is not transitive. X is equal to plus or minus y. Is this one reflexive? In other words, is x equal to plus or minus x? Absolutely. Is it symmetric? If x is equal to plus or minus y, does that imply that y is equal to plus or minus x? Yes, as well. We can disprove anti-symmetry by showing at least one case of symmetry. Let's say that 2 comma negative 2 is in the relation, right? Because it is. 2 is equal to plus or minus negative 2. In other words, we will just take the negative here, remove the positive, then 2 is equal to negative 2, and it holds. But if we reverse this, negative 2 comma 2, is this in the relation? Negative 2 is equal to plus or minus 2. Again, we take the negative rather than the positive. The negative 2 is equal to 2, which holds, and therefore the reverse also is in the relation. So it is not anti-symmetric, and it is transitive. And you can try a bunch of values for yourself, a bunch of pairs for yourself, and see that yes, it holds transitivity in all cases. X minus y is rational. So remember, a rational number is something that is an integer divided by another integer. So for example, pi is not rational because you can't take an integer, divide it by another integer, and obtain pi. Okay, so is x minus y rational? Is this reflexive? Does it make sense? Does it make sense to say that x minus x is rational? Well, x minus x is always 0, so yes, it is reflexive. Is it symmetric? Yes, as well. Is it anti-symmetric? No, right? Because 1 minus 2 is rational, but also 2 minus 1 is rational as well. So there's a case of symmetry, therefore it's not anti-symmetric. Is it transitive? I know we could do some math to figure this out. So if x minus y is rational, and y minus some new variable z is rational, then x minus z should also be rational. X minus z is just equal to x minus y plus y minus z, which is the sum of two rational numbers. Therefore, x minus z is rational as well. So we would say yes, it is transitive. So for this first one, D, x is equal to 2y, this is actually not reflexive. For example, we have, if we plug in 1 comma 1, this is not in the relationship because 1 equal to 2 times 1 is obviously not true. So no, it is not reflexive. Is it symmetric? No as well, because we have that 1 comma 1/2 is in the relationship, but 1/2 comma 1 is not. So 1 is equal to 2 times a half, but half is not equal to 2 times 1. So no, it is not symmetric. Is it antisymmetric? It is. There is no case of symmetry that holds. Is it transitive? No, right? So we have 2 comma 1, we have 1 comma 1/2, so therefore we should have 2 comma 1/2. However, 2 equal to 2 times a half does not hold true. Therefore, it is not transitive. And here's a counterexample. Next, E, we have x times y, which is greater than or equal to 0. Does this equation hold true on the reflexive property? Yes. Is it symmetric? Yes as well. Asymmetric? No, and we can give a counterexample. We have that 1 times 2 is greater than or equal to 0. And we also have that 2 times 1 is greater than or equal to 0. So, again, a case of symmetry, it's not antisymmetric. Is it transitive? No. Right? So we can actually disprove that by counterexample. Let's say that we have 2 comma 0, 0 comma -2. These are clearly both in the relationship, right? 2 times 0 is 0, so it's greater than or equal to 0, so the equation holds. 0 times -2 holds as well, but 2 times -2 does not hold. It's a negative value. It is not greater than or equal to 0, so the equation fails. It's not transitive. F, x times y is equal to 0. No, it is clearly not reflexive. For example, 1 comma 1, 1 times 1 is not 0. Is it symmetric? Yes, actually. Right? So for example, if we have 2 times 0, then 0 times 2 would also be 0. So in any case, no matter what values you plug in for x and y such that this equation holds true, reversing x and y, the equation will also hold true. Yes. Is it antisymmetric? For the same reason it's symmetric. It is not antisymmetric. Is it transitive? No, actually, you can even plug in these same values here. 2 times 0 is 0. 2 times -2 is 0. But 2 times -2 is not 0. So no, it is not transitive by that same counterexample we used for the previous problem. Alright, we get to the last 2 problems before we get done with the boring stuff, and we can move on to the fun stuff, which I consider the matrices and the digraphs. We have G, x is equal to 1. So we only have one variable here, which means we're only going to be plugging in the left value in every pair. The right value is just there. It's arbitrary. Is it reflexive? It's reflexive if for every value in the relationship, a reflexivity holds. Does 2 comma 2 hold? No, because the 2 is brought in, the right 2 is ignored. The left 2 is brought in. Does 2 equal 1? No. so it's not reflexive. Is it symmetric? No as well, because 1 comma 2 is in the relationship. Remember, the rightmost is ignored, but 2 comma 1 is not in the relationship. 2 is not equal to 1. Is it anti-symmetric? Yes, it is not symmetric in any case, except when 1 comma 1, but remember, anti-symmetry allows for the pair to be reflexive. So even though this is technically symmetric, one, reversed is still 1 comma 1, this is allowed. So it is anti-symmetric. Finally, is it transitive? Well, the only time when when some pair as well as its reverse pair are both in the relationship is when 1 comma 1 is considered. The reverse is still 1 comma 1. Does 1 comma 1 exist as a pair in our relationship? Yes as well. So this is the only time when the if of our transitivity is satisfied, and we even need to check for the then. So yes, it is transitive. Okay, finally for h, x is equal to 1 or y is equal to 1. It is not reflexive. For example, pi comma pi is not in our relationship. If we plug in pi for x and plug in pi for y, does the statement hold true? No. Is it symmetric? Yes. Is it anti-symmetric? And no. We'll supply a counterexample. 1 comma square root of 2 is in the relationship, and square root of 2 comma 1 is also in the relationship. So there's a hint of reflexivity. So therefore, it is not anti-symmetric. Finally, is it transitive? And no, we can give a counterexample. We have 2 comma 1. We have 1 comma pi, both in our relationship. Do we have 2 comma pi? Well, let's plug it in. 2 is equal to 1. That fails. Let's plug in the pi. Or pi is equal to 1. Well, the entire statement does not hold. Neither 2 nor pi are equal to 1. Therefore, it's not transitive in at least one case, and the relationship is not transitive at all. Okay, so now we get to the real fun stuff. We have a matrix here. Remember, a matrix can be represented with pairings as well. It can also be represented with a diagram. But we have this matrix here, and it represents a relationship, just like we've been doing this whole time. So for example, this leftmost quadrant, or I don't know, square, would be the 1 comma 1 pairing. This one right over here, this 1, would represent the 1 comma 2 pairing. So it's really just the same thing we've always been doing up to this point. It's all of the pairings. If that pairing exists in the relationship, then represented with a 1 in the matrix. So, is this matrix reflexive? Remember, it's reflexive if every single value in our set can be reversed on itself. So we have the pairing 1 comma 1, but we do not have the pairings 2 comma 2, 3 comma 3, or 4 comma 4. In other words, at least one value in our diagonal is a 0. So it's not reflexive in all cases. No. Is it irreflexive? It's irreflexive if there are no reflexive pairings. In other words, all of the diagonals are 0, but because at least one of the diagonals is a 1, we would say it is not irreflexive. Is it symmetric? Well, it's symmetric if for any 1 that does not exist on the diagonal, for example, this 1 right here, it's symmetric if every 1 has another 1 on the fold of that line. So this one could be folded across, and it would match up with this one right here. There's symmetry. This one is folded across and matches up there. This one can be folded across. Same over here. So it's symmetric for all ones. We don't have to check the zeros at all. It's like they failed the initial if condition, so we don't have to check the then. So yes, it is symmetric. In other words, it's mirrored across the diagonal. Okay, is it antisymmetric? Well, no, because we have at least one case of symmetry. It would be antisymmetric if every one corresponded to a zero. And again, we do not check the zeros, whether they correspond to anything at all. So it is not antisymmetric. Okay, is it transitive? Well, let's look at it more closely. We have the relationship 2, 1, down 2, and across 1. We have a relationship right here. We also have the relationship 1, 2, 1 down and 2 across. What that means is that we should also have the relationship 2, 2. Does this exist in the relationship? In other words, eyeballing the matrix, does this one and this one intersect at a 1? The answer is no. So this would not be in the relationship, and therefore it is not transitive. Is it reflexive? All of the diagonals are 1s, so yes, it is reflexive. It is not irreflexive because at least one of the diagonals is a 1. So no, it is not irreflexive. Is it symmetric? No, it is not mirrored across the diagonal. This 1 corresponds to a 0 when you fold it. So no. Is it antisymmetric? For it to be antisymmetric, all the 1s should correspond to a 0 across the diagonal. And in this case, this 1 corresponds to a 0 here. This 1 corresponds to a 0 up there. And this 1 corresponds to a 0 over here. So it is antisymmetric. Is it transitive? Well, we have the pairing 1, 2, and we have the pairing 4, 1. Looking at it more closely, we have 1, 2. There's a 1 right there, so it exists. We have 4, 1, down 4 and 1 across. It exists. The intersection of these should be a 1 if it were transitive, but it's a 0. In other words, 4, 2 does not exist in our relationship, right? We have 4, 1, this 1 matches with the left-hand side of this one, and we have 1, 2, but we don't have 4, 2. So, no. All right, so looking at this one, is it reflexive? Well, the diagonals are all zeros, so no, it is not reflexive. Is it irreflexive? For the same reason, all of the diagonals are zeros, so it is reflexive. Symmetry? Well, let's see. 1, 1. Looks symmetric to me. It's mirrored across the diagonal. Is it antisymmetric? Well, we have at least one symmetric pairing, therefore it is not symmetric, or is not antisymmetric. Is it transitive? We have 1, 2, we have 2, 1, but we don't have 2, 2. Therefore, it is not transitive. Right. We get to our last problem. We have a digraph here, a directed graph, and it represents a relationship. Now again, we can also represent this with a matrix. So for example, this matrix would be 3 by 3, right, because there are only three nodes, three values in our set, but we have it represented as a digraph. And all it wants us to do is list out the pairings that would represent this relationship. And that's easy enough. Our relationship would just be equal to A comma B, because A points to B, A comma C, because A points to C. A has a relationship with C. B comma C, and finally C comma B, because there's a little bit of symmetry right here, and so it points back at itself. Okay, we're done.